So hello and welcome to this Sigmund presentation on logical schema design that quantifies update inefficiency and join efficiency. It's joint work with Ziheng Wei. My name is Sebastian Link. So we will revisit classical logical schema design and look at some of its limitations, see how cardinality constraints can enhance a theory, to overcome those, and then look what kind of family of new normal forms they allow us to define, look at some foundations of the normal forms, and then see how they really quantify update inefficiency and join efficiency before we go over some algorithms for logical schema design. And the experiments will show how cardinality constraints can actually predict the performance of updates and joins before the database is even operational. So let's revisit classical logical schema design and see what the best is that we can achieve with functional dependencies only. So the general goal of normalization is to maintain data consistency and updates with a minimum level of effort required. And as a strategy, we don't want to admit any redundant data value occurrences in instances because they cause update anomalies. So the tactics is to basically transform functional dependencies that cause data redundancy into keys that prohibit them. In Boyce-Codd normal form, the left-hand side of every non-trivial functional dependency is a key. And we know that every schema has a Boyce-Codd normal form decomposition. So no data redundancy can be exhibited locally on single tables. But because FDs might get lost during the process, they still cause data redundancy globally across tables on joins of them. In the third normal form, we actually allow right-hand sides of functional dependencies also to be part of some minimal key, so that generalizes Boyce-Codd normal form. Every schema can be transformed into third normal form and without loss of any FD. So it's FD preserving. But therefore, some FDs still cause data redundancy locally because they weren't transformed into keys. So there's a natural trade-off in here. So ultimately, we can only quantify the success of normalization when no effort is required to maintain consistency, when everything has been transformed into a key. So that's only possible when an FD-preserving Boyce-Codd normal form decomposition exists. In all the other cases, the level of effort cannot be controlled nor even measured. As an example, here's a schema HEP, where a company is in charge of events at certain venues at particular times. There are some FDs attached with that. One company per event is allowed, one company per venue, and then some other FDs here as well. All the attributes are actually prime, so they belong to one of these minimal keys. And the schema therefore is in third normal form, and no FD preserving Boyce-Codd normal form decomposition exists in this case. Redundant data values occur. For example, here E to C causes every occurrence of kilo to be redundant, and V to C causes every occurrence of mega to be redundant in here. But actually, redundancy here means that the values are fixed. We cannot replace them by any other value without violating a constraint. And actually, the number of their occurrences is unbounded. So update of kilo is required in L1 different positions to maintain the consistency of EC, and similarly for mega. And L1 and L2 are unbounded a priori. They can be any positive integer. Even for Boyce-Codd normal form decompositions, we run into problems. So if we decompose along EC, we get something like this. We've successfully eliminated the redundant occurrences of kilo in here by transforming event to company into a key. But globally, we lost the FD V2C, which you can still see here. And of course, that would still have to be enforced on joins, for example, by assertion checks or on views. Otherwise, this would lead to inconsistencies in here. So updates are still required in L2 positions, which is still unbounded globally. So unless we really have an FD preserving BCNF decomposition, classical normalization can neither measure nor control the number of updates required to maintain consistency in general. So therefore, we bring cardinality constraints to the rescue in our example. L1 and L2 are really bounds of cardinality constraints. So for positive integer L, Cardinality constraint on X says that every instance can have up to L different records that have matching values on all the attributes in X. As an example, every event may have up to L1 combinations of venues and times. For example, 1000 in here. So that would be cardinality constraint. Similarly, venues may have up to L2 combinations of events and times, let's say up to 1 million as another cardinality constraint in here. If L equals 1, then X actually becomes a key in here. So cardinality constraints, of course, generalize keys. And if L equals infinity, then we don't really specify any bound for that attribute set. So this now leads to a new family of normal forms for logical schema design, which we call L-bounded cardinality normal forms, parameterized by positive integer L. So for every functional dependency that's implied by a given set and non-trivial, we demand that the left-hand side is bounded by L. Right, so this must be a constraint that is also implied in here. So in our example, if we look at these FDs in here, we can see that the left-hand sides here are bounded by these cardinality constraints, whereas the other left-hand side, they're all keys, so they're naturally bounded by 1. So this schema is actually in 1 million bounded cardinality normal form. So then that allows us to actually ask the question what the minimum L achievable is in a lossless L-bounded cardinality normal form decomposition, which would actually quantify the minimum effort required in database normalization to maintain consistency. So you could see that it depends on the implication of cardinality constraints and functional dependencies combined. Here's an axiomatization just of cardinality constraints. Here's the famous axiomatization by Armstrong for FDs alone. And then we can combine these also with some additional interaction rules in there. And the implication problem is still in quadratic time decidable. We get actually a strict hierarchy in here that's orthogonal to the existing hierarchy. We all know the hierarchy that every second normal form is in first normal form, third normal form and second normal form, BCNF is in between fourth and third normal form, project join normal form and fifth normal form. But then we have that one bounded cardinality normal form is of course equivalent to Boy-Scott normal form. But then this can be extended for any positive integer L and up to even infinity in here. So we get an orthogonal strict hierarchy in here. And at the bottom, we obtain full normalization with best update inefficiency and worst join efficiency, and vice versa at the top in here, fully denormalized worst update inefficiency and best join efficiency. Actually, locally, we can minimize L efficiently, right? So we can even decide in cubic time whether a given schema is an L-bounded cardinality normal form for a given L, because it suffices to check only dependencies in sigma, not all the ones that are implied. Then that leads also to a cubic time algorithm to compute the smallest L for which the given schema is an LBCNF. But if we fix a subschema in here, so if we look for a decomposition for a given L and ask whether this is in LBCNF with respect to a projected set of cardinality constraints and functional dependencies to that schema, that problem is co-NP complete. So then what do we achieve? Therefore, we deform what is an L update inefficiency. So therefore, a data value on tuple T in column A is L redundant when there are L distinct tuples in which the value occurs. And every update to at least one of these L occurrences results in a relation that violates some constraint. So therefore, the value is essentially fixed, right? So here we have our relation. E to C is satisfied, and kilo is 999 redundant, because no matter how we replace 999 occurrences of kilo, there's always one occurrence left, which then would lead to a violation of the functional dependency E to C. Right? So if we replace this, for example, all of the values by mega, this would be still violated. So therefore it's fixed and we cannot change it. Another view is if we don't know these values, we can still infer all of them just by looking at this pattern and knowing that E to C is satisfied. So then we say that the schema is an L update inefficiency normal form. If there's no relation that satisfies sigma, there is no constraint in sigma and no attribute for which a value exists that is L redundant for sigma. So we don't allow any L redundancy in any of the relations in there. And it's characterized by this statement. On the other hand, L join efficiency can be defined based on the famous decomposition theorem. So if R satisfies a non-trivial functional dependency, R is actually the lossless join of its projection on X and Y and X and the remaining attributes. So here, if we have the FD that E implies C, we can losslessly join these, obviously eliminating the redundancy on kilo in here. And then we can see here that kilo can actually join with 1k different values over times via the attribute party. So, and this is exemplified and materialized in this join in here. And then we call this number of occurrences L equals 1k in this example. We call this the join strength of this tuple within this relation in here. So that's known as a join strength, and therefore R sigma then is an L join efficiency normal form when the maximum join strength of any tuple in any relation over R that satisfies sigma is L. So this is a new nice definition. And then we can say, what are the achievements of L bounded cardinality normal form? Well, for any given L, the following are equivalent. So R sigma is actually an L bounded cardinality normal form if and only if it is an L join efficiency normal form, and if and only if it is an L update inefficiency normal form. So that is a very nice description of the trade-off between updates and joins and their efficiency. So we then have a suite of schema design algorithms, and we assess in particular the decomposition quality based on the cardinality constraints. So for the level of update inefficiency of a decomposition, this needs to be based on both preserved and lost FDs, particularly lost FDs, because we also need to maintain their consistency. And this might be the most expensive one. So it would be very dreadful to not take this into account, like, we can't do this in classical normalization. But for the level of join efficiency, that's only based on the preserved FDs, since we want to measure what joins are actually unnecessary, right? So whenever a decomposition is FD preserving, then of course these two levels would coincide. So we've designed an optimal algorithm amongst all FD preserving algorithms. So those, because of the preservation property, they require more schemata to achieve this. And we can actually compute the minimum L possible for achieving an L bounded cardinality normal form decomposition with that algorithm. So if we want to, have a schema with fewer, a decomposition with fewer schemata, then we can decompose alongside prioritized FDs, for example, those that cause a high level of data redundancy. But then we have no control over the lost FDs and therefore no control over the update inefficiency either. In a hybrid algorithm, we first apply opt, and then we sacrifice FD preservation whenever L can be reduced further by another decomposition step. So here we regain some control over lost FDs and also therefore some control over the update inefficiency as well. In our running example, coming back to the original question, what minimum L can we achieve? So if you look amongst all FD preserving decompositions, then we can actually achieve that L equals 1K. So you can see nicely in here how the redundancy of mega was eliminated, right, via the join over R2 and R3. And kilo still needs to be preserved to event company still needs to be preserved because of the FD preserving property in here, but we only require 1K. And the insight is in here that actually the FD CT to E is implied by these dependencies. And here embedded in CT to E is only the FD E to C, which is only 1K, which only causes redundancy of 1K. And actually the FD CT to V, which encloses the FD V to C, which causes a redundancy of 1 million, that can be eliminated because it is implied in here if we introduce CT to E in it. And then CT to E is, of course, this schema in here. So we've effectively reduced the redundancy from 1 million to 1K. By going over all of our schema designs that's achievable by our algorithms, we also get sort of nice logical properties with different and different decompositions in here. And we can even introduce materialized views. Materialized views are also informed in their selection by our design theory. So in our hybrid schema in here, we lost this FD, and therefore it's handy to introduce materialized view actually, like this. So to answer frequent queries of this kind, for example, but also to enforce lost FDs like this one on the view in here. And then again, our trade-off property is also intrinsic to the view, because the view has a level of, incremental update maintenance and join efficiency of 1 million. So effective join support, but updates to C on the base table R2 need to be propagated to up to 1 million updates on the view. So that's of course highly inefficient. We're not going to go over the different algorithms in here, but want to turn to the experiments. And the main outcome is here that CCs can predict the performance of updates and joins before the database is operational. So the experiments were done in this setting in here. And as a synthetic data set, we use the relation over our running example with 1 million and 1,000 tuples. So 1,000 tuples with matching values on E and C, 1 million tuples with matching values on V and C, and the other values were unique in the columns. As a workload, we averaged the performance over 100 different runs of updates and queries. And these are updates and queries that were affected by the functional dependencies that were present. So particular EC affects, of course, U1 and Q1, and VC affects U2 and Q2. These are the implementations of these two queries on the different designs, and even the materialized views on the designs if they were part of the investigation. So what turns out is that the specific updates and queries are best supported by different designs, and that the level of data redundancy for an FD directly translates into the performance for updates and joins affected by the FD. And this proportion also applies to the views. For example, in here, U2 and Q1 are fast on D1, but slow on D2. And symmetrically, then U1 and Q2 are fast on D2, but slow on D1. And the performance difference between these designs is proportional to the L redundancy caused by the FDs affecting this operation. So VC has this high level in here. Therefore, there's a high difference in performance of these update operations between D1 and D2. Similarly, then for the queries, as you can see here. And EC causes less redundancy, so the difference here in these trade-offs is also much smaller. The views act naturally, so this one leads, for example, to a speed up of Q2, but it significantly slows down U2. So this is in both cases large, whereas on D2, which has only 1K redundancy, the speed up of Q1 and the slowdown of U1 is relatively small. In the greedy algorithm, that performs well on U2, but not so much on the other operations. If we introduce views that speeds up Q1 with a small penalty for U1, and DH performs well for all update operations and relatively well for Q1. Introducing the view speeds up Q2, but actually slows down U2 significantly. When we change the settings slightly and have only 1,100 tuples with 1K and 100 redundancy, which is much smaller than the allowed 1 million, then the same workloads are best supported by the same designs compared to the first instance, but the actual cardinality is smaller, so the processing times are much smaller as well. Note that there are milliseconds in here. So observed trade-off actually becomes proportionally smaller. So the observed trade-off in update and join performance on the physical level is essentially testimony to the ability of cardinality constraints to predict such behavior during logical design before the database is actually operational. So we've introduced a hierarchy of these normal forms that can quantify update inefficiency and join efficiency at the logical design phase before the database is operational, is orthogonal to the existing hierarchy of normal forms, can even differentiate schematas in third normal form that couldn't be differentiated by FDs alone. Algorithms generate schemata with different properties. CCs can predict the workload performance at the physical level, and our measures of update inefficiency and join efficiency also inform the view selection. This is some of the extended work to extensions of the relational model, and here are some of the references. So thank you for watching.